Okay, so the next speaker is Nitin Shukla. So Nitin got his PhD in computational plasma physics in Lisbon, and after that he joined Cineca in Bologna. So where he's involved in developing and deploying parallel codes on modern HPC systems. And today he will start showing you something about. I mean, is it on Leonardo, right? Already. So you will start seeing some uh, hands-on sessions on Leonardo, and he will also talk a bit about compiler directives to accelerate applications on GPUs. So just remember, this is 2 hours. Then we have the break. Then we have other 2 hours, and then you have the mentoring. Okay. So if any of you want to present his work, his or her work, me and the other 2 hours plus 1. Okay. And then we have the mentoring. So if any of you want to present or discuss his or her work, we'll be here and giving feedback to people. Okay. So you're welcome to join. Thanks.
Can you hear me, right? Yeah. Okay. Okay. So thank you very much for being here. If you survive until now, I hope that you will survive next 4 hours. And so I was really thinking about what should be my starting point, because since morning, and the danger is when you are talking about HPC, GPU, you're going to hear a lot of things which is cyclic, right? So it's like if you have seen keynote presentation of Google, last one, there was someone clip and say AI, 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 AI. So end of this school, you will listen HPC, GPU, HPC, GPU. Okay. So bear with me. I have there are a couple of things might be repetitive, and that is my this was my biggest fear. So I had to up my game and try to modify my project in such a way that it can bring novelty and actually what justify for you being here in the school. Okay. I'll try my best. Let's see how it goes. Okay. For my so I start myself like I'm not computer scientist. Disclaimer. I'm a physicist. When being a physicist was fancy thing, right? Not computer science, not data science. I was one of them. I started my career as a theoretical physicist, and then I moved and to Instituto Superior Técnico, Lisbon, where I did my master in physics engineering. I did try to go to experimental one. I took nanotechnology. I got bored and I went out. I thought, no, that's not for me. I stick with computers. I found it interesting and I could do things I like to do, solving problems. That's it. So just a little interesting story why I end up in HPC, because for sure I have no skills to working there. It looks like. I won a grant, 1 month grant. This used to call Europe HPC 3. I went to Cineca, met amazing people. I finally see what these people do, because I normally run my simulation and I don't bother. But I find out that I can do a lot of things. And I think if you're doing PhD and you are involved sort of parallel programming, your job is secure. There are a lot of things going on around Europe, and actually they are looking for people. So if you're thinking career in HPC, I think is way to go. Enough about me. What is my role at Cineca? Started working with Eurofusion, where for as a high level user support. In fact, me and my colleague Alessandro, he was the first person I started to work, and it was Marconi Cento was the first machine that I had full access. And just like a young kid, I thought, wow, I have whole system for myself. And we were doing benchmarking, playing with the machine. But where I things got interesting to me is when I moved to other project. So I work basically porting codes, optimizing sort of things, which is not fancy enough, like AI or whatever. So this talk is going to be HPC minus, not hyphen, AI, okay, on dot. Now, what my role is in this C project, it's basically they are very similar. I look at the code, try to help code owners to put their code on GPU. The main um, um, project which I kind of lead from Chineka side is Space COE, and some of my colleagues who are doing PhD or postdocs, they are also in this audience, and they are kind of aware of this. Apart from that, I get to teach, and I'm a DLI certified instructor, not working for NVIDIA, for Chineka, and I do the mentoring for a hackathon, and also just finished the GPU bootcamping before coming here. So since I told you space, and space is just scalable parallel astrophysical code for exascale computing. Um, they are in this project. I started in 23, and it's almost 4 years that's the life of this project. And what we want to achieve is there are some open source code, and what you would like to have that they can run or take advantage of exascale computing in the future. And these are the partners. So advertisement is important. I learned from Americans. So watch out, all these people. And these are the code. Okay, you can see the diversity of this project. I get to work. Let's say Chineka is involved 3 code out of 7. So Pluto, OpenGadget, and IP 3D, which is space plasma, which is sort of my background is. So objective already said, so I don't need to say more. If you want interested to know, please go to their website and look at it. There are a couple of hirings as well, so you can look at IT4I. They are hiring in this project. Just a bit of advertisement. Roadmap. That's where I want to go. So why are taking so much trouble learning new things? Learning new things is pain. So what is the best way? If you're here because you want to get all the information so that you can accelerate your interest and do things, right? So what I will focus on heterogeneous computing, sort of what you are hearing since morning, and what the program was light OpenACC. I thought, why light? Maybe after having lunch, you can be, you need kind of a low dose. So OpenACC, that what I'm going to speak about, and mainly focus on why you should use them. Some of you are familiar with this, but nonetheless, since you're here, you have to listen. Um, what is the student model, memory model, what are the benefits, some limitation. There is a case study. There will be two exercise, hands-on, not exercise, hands-on, which you try yourself. And I think the way I want is that just think like this is a mini app which you starting from scratch, you will profile as well, and sort of thing that you'll see. So this is wrong. What I wanted to, yes. So in the last part, I would like to show just a, let's say, comparison with CUDA, if you know, have a background, and how easy in translation to OpenACC. And then, since I saw some speakers, they already talk about their research, and I took some of my previous slide. I just recycle it, and then I think I would like to show you what go are. So if you want to download the exercise, there's solution, there's makefile, readme, everything is there. All you need to do, zip it or clone it, whatever. Put it on the Leonardo. You have to ask for interactive node. We are going to use only one GPU. And so we are not launching, submitting any jobs, right? So you are going to be very fast. I give you a couple of seconds. If you're all good, I go ahead. Okay. So why GPU? You there is uh, there is no magic answer. Why not? But look at this top 10 system, and you see that most of the GPUs are equipped with, most of the HPC systems are equipped with GPUs. If you combine first and second cluster, you will see that about 70% of flop per second is done by GPU. And what is interesting is that you look at the other system apart from Fagaku, most of them has varieties of GPUs. I mean, first one is AMD, then I think it's Intel, then there is NVIDIA GPU, etc., etc. But if you see the kind of timeline, and I would like you to focus on some point here. You do care about peak performance, right? You really want to go beyond this, but there is a cost of this, and we have been constantly pointing out what it be. Um, the sorry, the main point is that there is a cost of such a large system, um, power and space. You see, going from 6 to 12 megawatt, from 5,000 to 10,000 feet square, to if you go up to, let's say now we are here, you are actually going to 20 to 30 megawatt, okay? And look at the size. So both, there is a limiting point where um, you want to take consideration just having a large system when you want to do a lot of computation. Um, but what they really deliver basically is driven by the application. And if you look at this graph that you have seen many times, that is the golden era of CPUs and where the GPU came in, etc., etc. What is interesting is you heard Moore's law. There's another law which you'd like to hear is Denner's law, that says that power per transistor should go down, but it was true until 1997. It faded away. So now it looks like you can just um, um, go on this scale. So somewhere you can find a plateau. So you really need to do something else. So future computing is not, you just want to solve a lot of problems from all the areas, right? So if you, and it requires not changing only the hardwares, but also the programming or developing new things, for example. And this is how this graph actually illustrates. If you want to know more, please look at this reference. The question is, what really stop building new clusters? When we talk about ASCII scale computing, what we mean is means that a computer that can solve, uh, that can calculate at least 1 quintillion fold floating points operation per second. That is one after that much zero. Okay, so keep in this mind. You see, we reach to peta per second. Here, this is more or less where conventional cluster, just with the embedded a lot of CPUs, we broke down, and we want to go beyond that. So I stress this point that we need to worry about energy, and if you want to build such an XSL system, how much energy you need. And thanks to NVIDIA, they advertise this slide, is that in order to build exaflop supercomputing center or cluster, you need to burn this amount of energy, the power of the Bay Area. Okay, so I think it's good enough to give you motivation. Is that not that we want bigger and bigger system, but we care about nature, right? So electricity is important. But why GPU is trending? There's another scaling that you can see. There's an order of magnitude difference. You see the GPU computing curve is increasing, and there's a kind of prediction it goes 1000x in 2025. Okay, so that's quite impressive. And there are studies on that to understand. It's just not a claim, but it's something real. Initially, if you look at the GPU computing, GPU per se is not about the scientific computing. It was driven by video games, basically the gaming industry. And there was a paper. I didn't mention the reference. Sorry for that. But it shows left side theoretical peak performance for single precision, theoretical for different CPUs, NVIDIA GPU, AMD GPU, and you will see that GPU for the flop per second is winning over. There are better plots, which is Daniel has showed, but I thought this was the published paper, and I think was good to highlight here. But there is also theoretical flop per cent, how much it costs, GPU versus CPU, and you can see here. But why accelerator give more? Why CPU doesn't give higher performance? You saw that if you look at this equation, P is equal to V square times frequency. So there's the cost of this. So you can do a lot of computation. You just have to increase the frequency. I mean, the more powerful CPUs are, the frequency is higher. You need to feed more and more energy. Okay, and that is not, let's say, practical. Okay, that's another thing. And then last 10 years, they measure the energy efficient for HP architecture, and you can see GPUs are quite the heterogeneous system, which is CPU plus GPU, are um, quite efficient. Okay, so that was how HPC evolved. And so what changes for programming model? So if you look at single CPU, where you had one CPU has its own memory, you just need a serial code, some application, you measure performance in a megaflop per second. You wanted more, so you build a system which has CPU which has it's like shared memory. So you need a new standard to program such system like OpenMP that you learn, or pthread, and you achieve gigaflop per second. This is what you heard, distributed computing, which is that OpenMP is not enough. You need more than this. So when hardware changes, also you have to adopt a new standard to program system. Okay, so you can take advantage of MPI plus OpenMP, and it was good enough to achieve teraflop per second. So if you learn anything from the history, is that when hardware changes, software also need to be changed. Okay. So then CPU is almost, let's say, plateau, and where the GPU started to kick in. It shows this sign, the new light of performing computing. So when I say GPU, is not only the heterogeneous, but like you can have a different hardware that connected to CPU, and you can do different program to, like, you just listen in the first stage. So, but I'm going to focus only for GPU. That's why I'm keep repeating GPU. Leonardo, this is what you're going to use. And look, Leonardo, I think in 2023, right, achieved the highest ranking in the world. That's ever for Chineka. And if you see that impressive number is, you could do 240 petaflop, and we have about 14K GPUs. Okay, that is quite impressive. Where we are, our new place is called Technopolo. This is what sort of things have been shown previously, and if you want to find us, you can come here. This is how you say, artistic view, but this really looks like this. I mean, it's huge. It's amazing. So why GPUs are training? That's where I want to go through. So if you look at CPUs, CPUs and GPUs, they are designed for performing different tasks. They both are silicon based. So you see the in this cartoon, what you're looking at is left side, um, some cache for CPUs. So the large silicon is dedicated to cache. So CPUs are caching, right? And if you want to process data caching there, and if you want to process just data processing, you need to have a lot of ALUs. And this is how GPUs started to come in. So the most of the silicon was dedicated to ALU instead of cache, right? So this is something where people start to reflect on that you need, if you embed lot of ALUs, you can do a lot of parallel tasks, and this will be high throughput. And the reason that why the caching was important for CPUs is basically these CPUs, they are um, they are quite heavyweight. Let's say if you look at the frequency of CPU is 40 gigabyte, and GPUs are about one, around one. Okay. The point is that when you have more threads on fly and you don't have enough resources, what happens is that operating systems try to do context switch, and in order to keep large data for a given time to execute, you needed a cache. So that's why the most of the silicon was dedicated there, and you could do um, um, concurrently lot of tasks. Um, so that means you could do a lot of heavy tasks like like you're running email, whatever, Teams, etc. There is a concept switch. So operating system decide in order to let everybody goes ahead, it has to free some space to other tasks. However, GPU does differently. GPU doesn't launch one thread; it's launch group of threads. You heard it called warp, and you don't launch any serial code. You launch parallel task, and you launch a lot of them. So if you look at W1, W2, W3, W4 is a group of 32 threads on NVIDIA GPUs. And for the given time when warp 1, so GPUs consist with a lot of threads and lot of registers. So if there is a context switching between one warp to another warp, um, it's you don't pay the penalty, because for some given time you do a lot of computation. That's how you can hide um, um, the the latency, and you get high throughput. Um, Again, this is NVIDIA slide where they distinguish between speed versus throughput. And the idea is that you, if you have to bring 100 people from A to B, Ducati is faster, right? So, but you can just hire a bus and embed it, put everyone there, and yeah, so you can get to high throughput. But I think the best introduction to GPU, why GPU is powerful, is basically this video that Leonardo. This is the best introduction to GPU you can think of. Just 1 minute. So
Leonardo. When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes within which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the most.
this is like 2015 or something like that.
Painting demonstration. And 10, 9, 8, 7, 6, 5, 4, 3, 2.
Come on. That's it. That's what GPU does. So, you okay? So the summary is GPU is high throughput. I already told you if you look at the clock speed of CPU is 4 gigahertz, and actually the GPU cores are basically weaker than CPU. They're not meant to do any sequential task. They're not meant to do any heavy thing, let's say, but they would like to do some. These are lightweight threads, so you can perform them lot of parallel tasks. What you get in GPU is high bandwidth. It's not only you're getting ALUs, this is also quite important. And other things, I don't want to read it. You can read it yourself. If CPUs are so good, why don't we just use, sorry, if GPUs are good, why don't you use only CPU? There is this map this chart that you have seen. The point is that what you would like to do is to migrate a task temporarily. So you do some tasks there, but CPU has a lot of leverage. That's why we call heterogeneous system, because they are really do different hardware. So although if you look at CPU architecture, they were very easy to program. Now you understand OpenMP, MPI, this was good enough. But to program such system, you really needed to think a different way, because both CPU, GPU have a different memory space. So that means your application is running on some given time. When you find the computation, which is computationally very intensive, you migrate to the GPU. When task is done, you move back the data to the GPU. Sorry, for the CPU. And there is a ratio of this 20-80%. You see that in your whole application, at max, you will see that 20% is the part that you are offloading to the GPU. Okay, so you already heard parallel programming is all means divide and conquer, right? Is the only gospel truth how the whole world moves around, right? So what you like to have is let's say your loop iteration space. You want to chunk them, and you want to assign a lot of threads that they can do. Parallel tasks. But we also heard that we cannot just uh, subscribe lot of threads, do the whole application um, on the LATAR thread. There is a limitation, and the limitation is Adam's law that will be always follow. At least until now, this is always following. So just a little bit about GPU architecture. It being used for the rendering, and if you look at those GPUs, they were basically doing simple transformation of position, generating some pixels. So you could do kind of mathematical multiplication, all sort of things. And this was initial GPU were not programmable, so NVIDIA came up with a GPU which was about 92,000, something like this. So, but they had to kind of do something else to program those hardware. So they invented CUDA, and there was support for the libraries as well. Then you have directive approach. All sort of things started to pop in, and then you will see that nowadays this is how the journey of heterogeneous system is. The two main part that you would like to keep in mind is main memory, which is analog of CPU server. And if you look at the size, more or less, depending on the GPU, you can get from 16 to 40 gigabyte. They have very high bandwidth, this is something that you have to keep in mind. There are a lot of threads. They are independent cores. They have control units, and they call streaming multiple processors. Okay. And if you just zoom in, you will see there is a PCI interface, memory control, These are the graphic processor clusters. These are your streaming processors, and there is your NVLink. But let's zoom out before more. You will see that there is schedulers, and you are doing floating point 32 core, and you are also doing some tensor operations. There's a ray tracing and all sort of things. Okay. There are two types of GPU you can get. So you can, if you're if you're looking at the scientific application, you do have to worry about correctness, right? So this is where the first one comes in. Only the GPU gaming one, where you're not worried about precision per se, right? You just want to render and do the computation. Prices can be more expensive for for example, high performance computing. You don't need a lot of GPUs or lots of computation power for the video games. I mean, fairly you could play uh, um, on your laptop. You don't need a whole entire Leonardo to play, let's say, for example, but they are not meant to do that job. Okay, so GPU architecture is basically this. So what is GPU it's a consist of multiple processors are these CUDA cores. So that is called streaming processors. And uh, this will be more clear to you when I go to OpenACC and I'll talk about open optimization. You have to keep this in your mind. There is a reason why I'm showing this plot. So GPU execution model. I already told you there are two different hardware. That means CPU is a host centric. So if you open a blade, you will see your CPU is here, DRAM is there, GPU memory is there. So you need to find a way to launch the kernel, but also move the data so that GPU can do computation. And this is why heterogeneous computing become a little bit complicated. It's always you think that you have a lot of ALUs, have a high bandwidth, but you still your code is not performing well. So when you launch things on GPU, it goes to the global memory of the GPU. Then the data is sent to the two ALUs. When do the computation, they have to move back. So you see there accessing memories is expensive. Moving data is where the bottlenecks is. So we are not talking about only NVIDIA GPU. There are more GPUs, there are more models that you can think of. There is a paper by Anton, Andreas from JSC. He actually did very good job to kind of compile everything, what type of GPUs are, what programming models that you are it's existing right now. So you basically have three vendor, two major players, let's say AMD, but I don't want to make angry anyone. You have Intel, AMD, Intel, NVIDIA. And if you look at their native programming model, in the morning you already saw SQL, that is Intel native programming model, CUDA, that's for NVIDIA, and HIP. And there is some community approach as well, like this OpenMP, OpenACC, Cocos, rather. You have two major language, C++ and Fortran for scientific computing. And if you look at the possibility, you get this this number, like you don't know where to start, right? So the color shows on each hardware which supports or not. I mean, there is also Python, but I care less about Python here because I'm just talking about scientific computing. We're focusing on language C and C++. So this is how it is. So CUDA, if your program consists with CUDA, your code is ported with CUDA, that means you're limited on hardware. So you can run only on NVIDIA GPU. But the translation between CUDA to HIP is very easy. They made it kind of identical. So you just replace from CUDA to HIP. It would most let's say if everything is the same, it might work also on AMD. Then there is SQL. I think you heard in the morning. The I think only good thing about SQL is that it's like GPU agnostic. You don't care about which GPU you are running through, but you should be able to run your application. That is what I understood the application. Then you have this um, OpenACC directive approach, OpenACC, OpenMP, and standard. OpenACC, OpenMP, they are, let's say, most known, and let's say OpenMP, you already heard what it is. They are very similar in nature. Then you come again in this loop, which one is better, right? Then you have other libraries that you can use to offload your code. So there is these three ways looking at how to program a GPU, and basically you're binded by either your approach to get maximum performance, or you just want something very easy, right? Just using some libraries, and this is what it shows. So if you want maximum flexibility, that means that you can use you can utilize hardware efficiently. You can use, for example, CUDA or HIP or OpenCL. This will require time, so it's not that's something that you can achieve in 6 months or so. It can take a year or more than a year. But there are other approach. So yeah, so that's all. Yeah. So there's a other approach that is a drop in acceleration. So that means that more other libraries, they have support for, like if you look at PATC, PATC is supported by CUDA, also HIP, so you can run on just using library. You can run on any other GPU that you like. You at least you have. But the one thing is very interesting is OpenACC, where or OpenMP is, where you like to put um, um, effort, where you can let's say within 6-7 months, or if you work constantly, at least you are able to run your MPI plus OpenACC code on the GPU. And this is why OpenACC is, or OpenMP directive approach, kind of find a balance between productivity and um, the performance. If you're ready to lose your 20% or 10%, I don't know, but just speculating, 5% of your performance or 20% of performance, CUDA is always going to win, HIP is always going to win. It is very abstract, high level, so you don't have that much control that you would like to have as a programmer. But if you're if you can sacrifice 5-10% at max, but you can offload your code within 6-7 months, that means you can solve your problem. You're not worried just to develop things. This is also can be one way of looking things. Okay, so I go ahead. So that's what I'm going to talk about. So now you understand where I'm going to, why I'm looking at compiler approach. So what I meant by Axe is basically OpenMP. Either you use OpenACC or OpenMP, right? Both are directive approach. There is a subtle difference. You will know with experience. It's not straightforward. But if you are a programmer and you want your code to run, what you have application, you have access to GPU, use OpenACC or OpenMP, and you're good to go, right? That's how easy it could be. And you really want to fill this gap, right? So in order to cross this bridge, you can take a different path. But easy path could be OpenACC, OpenMP. Question: are you familiar with directive based approach, parallelism? No? Kind of? Okay, I think you are, right? Just yesterday you saw OpenMP, and what this OpenMP is basically telling compiler, please do something on my behalf. If my code is serial, and I put some pragmas. I compile with right flag. I generate a Peller task, and on runtime, okay, you don't launch one thread. I mean, let's say you launch 6 thread or 7 or I don't know, 32 thread. You're doing Peller program, some sense. One question: which thread lives from beginning till end? That is your master thread, right? So everything starts from master thread, which has a unique identity, index 0. When it hits the Peller region, because we follow this fork join model, you spawn a lot of threads. They do Peller job. They must synchronize, and even the thread that you spawn, they can become a master thread. They can do a nested loop, and this is how OpenMP is, right? This is whole model of OpenMP is. So when you create OpenMP thread, you see there is a sequential part. That means at that point, all the threads must synchronize, and the thread that you have created, they will be destroyed. Okay. So from beginning till end, only master thread lives. Okay. All right. So if I do that, so what I have done in program, I look at my loop, most complex part. What I did, I just put pragma OMP parallel, right? At this point, I just created a lot of threads. That means your entire iteration space is going to be redundantly done by the number of threads that you are allocated for that loop. But that's not efficient. What we want, divide and conquer. So you could do something like this. You can, sorry, I went ahead. You can manually decompose iteration space, or you just take the look at the specification of OpenMP. For is the one which divides your iteration space. It means that each iteration space has different data to work on, right? All right, so this is why this slide is important. Serial total time will take time for a single iteration times n. If you allocate 4 threads, they are going to take more or less the same time, because each iteration is done by all iteration is done by each thread. But if you divide them, that means this part is different data set is given to each thread. That's how you could reduce the total time. And this was good because this is supported by OpenMP, supported by most of the compiler. It's very easy to compile. It's easy to understand. The problem is the debugging of OpenMP. It's really pain in neck, right? It's not easy when you are really working with hybrid code. So now, what I plan when you do exercise, and actually kind of I want to follow as a benchmark for yourself, I want you to think like this. You have NVIDIA system, right? GPU you are going to use. So I want you to use NVHPC, their compilers. So you're not changing your compilers. You're going to compile your serial code with NVHPC compiler. Then you're going to compile OpenMP code. You try to offload OpenACC, and you see the comparison how they are. So how do you compile a serial code? Just like this, very easy. Call load module NVHPC, and you put minus MP minus 5. Okay, so something that you would like to optimize. If you're using C++, just put N C++ or Fortran NV4. Very easy to compile. So if you have existing OpenMP code, do you think you just adding NVHPC, right compiler, right flag, can you offload your code? Anybody? Huh? No. Question is, will your legacy OpenMP code, which is already optimized, you have GPU to access, you have a compiler, you put right flag, can you offload your code to GPU? Can the same code run on GPU? Of course not. That's true. It will not work because you have to do something additional thing. OpenMP was not meant to program a GPU, right? So this is where OpenACC, OpenACC, they are similar. And if you look at their history, when GPU were becoming, let's say, easy to program, where community thought, basically this university in US, what was the name? Before it was PGI compiler, Oregon University, I think. No, I don't remember. Yeah, they grouped together and then they actually targeted um, um, accelerator. So they started to work on OpenACC. But if you look at the timeline for OpenMP, the each timeline just shows the specification for OpenACC or OpenMP, right? So somewhere here where OpenACC diverted, and what I heard from the expert, there was a kind of unspoken deal that they should combine, but I don't think so they're gonna combine ever. But OpenMP really then have the support for GPU. I think it's OpenMP 4.5 where they actually add directive for OpenMP, so they could actually you could program GPU so using OpenMP. Okay, that slide is very easy. It's if you search what means specification is standard, it's English. There's no debate. You know what it is. Why am I saying this? Because this is how I want to differentiate OpenMP or OpenACC, right? OpenMP, let's say, is standard, right? It may work everywhere, right? May not be, so it's portable, may not be true that you get same performance everywhere, right? If this is what you care, good. OpenMP, easy to do, go for it. But if you care about specification, like if you're using NVIDIA GPU, use OpenACC. There is no, they will always outperform OpenMP. And there's similarity and kind of, or let's say, where they are not similar is, I already said, they are directive approach. That means both for OpenACC or OpenMP, you are hinting compiler to do something. That means they should follow more or less the same ideology, fork and join model. If you look at OpenMP, I already talked about that, but OpenACC, just putting up means that you're migrating tasks to a different hardware. The main difference is prescriptive and descriptive. So OpenACC, if you're using, let's say, NVIDIA GPU, so where I want to go is like you have the same compiler and you have the same hardware, right? Think like this, and you say what I need to use. So if I'm not selling NVIDIA GPU, but I'm just saying is that use just OpenACC because your performance is going to be better. So prescriptive means programmer explicitly parallelize the code. Compiler has to obey. Descriptive means you tell compiler, compiler parallelize the code with some guidance, but you don't need to track everything. This is what OpenACC does. Basically, OpenACC, you do things, maybe you are thinking this is the best way, but compiler is smart enough, it can do better job than you, right? So where it has to parallelize, it will parallelize. If you think that that part of the code shouldn't be parallelized, is not optimized to vectorize as code, it will not do, right? So it will do a lot of optimization on your behalf. That means you have very little things to say as well. But for a given set of compiler, I think what you want to achieve is the high performance. That's the cartoon that you have. So you start your code from a host. So now CPU has name called host, GPU has name device. Okay. This is the terminology that NVIDIA coined beginning at the beginning. You will see what you do. From the host side, you have your Pragma OMP parallel loop is running on your CPU, but now you have a very computation intensive part. You want to offload that part of the code. You put target device that will expose parallelism on the GPU. That means you're going to launch team of lot of threads. They have to group together. Remember block that I showed, multiple processor and core. This is where I'm going through. It can also run each block. It can have some SIMD instruction as well. GPU programming is single instruction, multiple thread. That's how it follows. If you look at OpenACC, it's more or less very similar, right? They have a difference in name. The group of threads they call gang, but what you put some pragmas for OpenACC to expose parallelism on the GPU. And how the code looks like, just very simple. Left side is OpenACC. You see Pragma ACC directive for C, for Fortran, and there is for something you have to add target directives for OpenMP. Very easy. So when you add this, like you see, you can build a macro where you can on compile, either you switch to a OpenMP or OpenACC, you can compile both, right? So you can use either you want to use GPU or CPU. So Pragma ACC parallel, that means it's going to expose a theme of lot of threads, which called gang. And if you put Pragma OMP target, that means you have a lot of threads that call teams, right? Just nomenclature. Okay. But, okay, so what I'm going to focus, juggling between OpenACC, OpenMP is kind of confusing. So I'm going to stick with OpenACC now. And so this is what I'm going to speak about. So OpenACC, I'm going to read that because it's very straightforward. OpenACC is a directive-based parallel programming model designed for performance and portability. That is the main goal of OpenACC was. And you can compile the code for specific hardware, right? So you can compile your same code for the CPU, but also for GPU, for other hardware if you want to. Why it's easy and why they find this balance? First, it's incremental, so you have a single source code. You add pragmas with right compiler. Compiler knows what to do. If you remove flag, your serial code is still there. When you start to develop things with OpenACC, you are not going wild because now you think, oh, it's so easy. I will put pragmas, I will put data clause, and put everything, and you will find yourself that it's not very efficient. What you like to do, actually, you progress incrementally, look at your profiler or compiler feedback, you go back again, change, do it again. Single source, what I said, is like if you remove flag, you still can maintain your serial code, so nothing is you're changing. So if you know CUDA, you have to do a lot of change. If you have seen SQL, you are changing. It's not given that you're just adding things. Where OpenACC is good is the simplicity. Okay, sometimes what you like have something to be done in a very simplified way. It's not idle, but like I think this is the way to go. Low learning, you will see end of this this whole course. You say it's very little things to know. I don't need to know a lot of things. I don't need to track all the global index in a CUDA. I don't need to know how many blocks of thread I'm launching. I don't need to know when I'm moving memory. Nothing. Everything will be handled if you understand what things is. What are you doing basically? So why OpenACC? All good qualities doesn't mean that it's life is as beautiful as you think. I already talked about performance overhead, limited control. Of course, this is something that I already talked about. But seriously, what you want is a code that you can and you are able to use a new hardware, or let's say, for example, here we are using GPU. So the case study is this Laplace 2D, which you might have seen in another your course. It's very famous and abusive one at the same time. But all you need to do, what you want to do is you have this plate that you want to see what would be the temperature for a given space in future. And the code is pretty simple. It's solving only this. It's just adding. If you want to know what is the value of AI and J, you just have to sum both and divide by 4. And the code description is quite simple. You have some tolerance here, while some it has to converge somewhere. But then you have this loop where maximum computation is done, right? You are computing NU, that's the equation that you are solving, but we are also swapping input and output array, right? So there's two simple loops that you are doing. Now, I want to be system agnostic and compiler agnostic. So I'm sure I'm not changing a lot of variables. I want to make sure that I'm running 1,000 iteration space, iterations. So when I do that, when I compile this code, NVC without any flag, and I run my code, this is what I get, right? But if you know a bit about how to profile, you can actually tag those blocks while, for, and you can bisect how many, what's a percentage that it takes more time, right? And this is where you look at your code. So what you're doing, you're identifying the place where things require more effort. So you're going to assign more team of threads, okay? So at this point, I can ask you to do it yourself using OpenMP, compile on your now, but I wouldn't do that because I think I want to go a little bit more, and I want you to start using GPU. So I'll just tell you the answer is just here. 2-line, you parallelize your code. Pragma OMP, parallel, shared is not important, but let's say it's good. Reduction is important, just there. You could remove shared and you can also collapse. You have seen all the feature in OpenMP, and it's not necessary that you need to know a lot of things about OpenMP, but if you know, it's ice on cake. So you can just eat it. All right. So now I can do kind of my benchmark. So I can try, when I compile this code, I can allocate 1 thread, 2 thread, or 32 thread, and you can see at some point it's going to peak. You cannot push further. Now, when you're talking about GPU programming, it doesn't matter if you're using SQL, it doesn't matter if you're using CUDA, it doesn't matter anything. If you're using two different hard system, basically this is inbuilt two different cluster, CPU cluster and GPU cluster. They have different memory address space. That means you need two things. Exposing parallelism, moving data. That's all you need to know, right? So we are going to expose parallelism using OpenACC, which I already hinted. So if you just put pragma OM ACC parallel, it generates a lot of threads. But you see at this point it's not efficient because all the threads, the compiler can generate one or many. Yes, please. Yeah. Uh-huh. Why? Yeah. So Adam's law, right? So what really happened? Now I'm going to write, okay? I don't want it to write. 1 minus P divided by N, right? If this quantity is too big, this is going to be small, right? So at some point you will kind of find a asymptotic behavior. I will never meet. So it's just math theory. So it's not going to change. But yes, then you can have a bigger system size, and but I'm saying what I told you before. You want to fix your problem size, and then you are changing allocating more number of resources, team of threads, right? So at some point they are going to be like MPI. If you do MPI benchmark, if you are used to it, No, obviously, yeah. Now you increase more, you can allocate more. Yeah, for this particular given iteration, which is 1000, is speaking at this point. Okay. So at this point, you're doing a very useless job. All threads, team of threads, they are doing exactly the same thing as OpenMP is doing Pragma OMP parallel, right? It's exactly the same thing. Now, so but idea is that you want to parallelize the loop, right? So you can add ACC loop, and now you can see that let's say this team or gang have a lot of threads. Now they are divided. So iteration is divided by each within each block. This is very similar to OpenMP. If you use is target OMP for, right? You can have also nested loop, and you can use same Pragma ACC loop, Pragma ACC loop here for OpenMP. Is it true? That is good. In OpenMP, nested loop is disabled by default. You have to do something else, right? In OpenACC, you are allowed to do it. So you see one more difference. You will see more difference as I go along, right? And then I have a slide which just translate OpenACC to OpenMP. So you have OpenACC, how easily you can transfer to OpenMP. There is something called kernel construct. Okay, look at this this embarrassing parallel code. Pragma ACC kernel, Pragma ACC loop. There is no explicit things in OpenMP. You can have a multiple loop right here. So what compiler will do? Compiler will do, it will generate one kernel, as I said to you before. Compiler has a lot of leverage, so it decide it's good to have one kernel or two kernel, right? It will decide how he thinks or she thinks it's better. You don't have the same thing in OpenMP, so there is no kernel construct. But for parallel loop, when you instead of kernel you use parallel, you are exactly telling kernel that if I put OMP parallel, then ACC loop and ACC loop, I want you to generate two kernels, right? So now you understand this. So there is a subtle difference. Kernel compiler has a lot of leverage. You don't have it's not guaranteed what you're telling compiler will obey you, right? But compiler will guarantee the correctness of result, because although it can optimize things, your loop, but correctness is very important. It can fuse to nested loop and make it one, for example, right? Contrary is not true for parallel compute directive. So how do you compile OpenACC code with NVHPC? So OpenACC fairly supported by other compilers as well. You can compile with GCC, just adding minus F OpenACC, but you have to add additional thing. You see, you have minus offload, then you have to add some other part. Same thing for Cray. What is important for us is NVC. What you need to add is minus GPU is equal to target. This is where target architecture. I mean, this is where you add whether you want GPU or sorry, either you want to compile for host, adding like multi, I think called host or something. You can look at the documentation. You can compile the same code for your CPU, not for GPU. But just adding minus ACC and then minus GPU, and you know that each GPU has specific compute capability. That means it has some weird number CC80, CC70. Like, and if you just load module on Leonardo and you put A and B HL info, you can see all the specification of our GPU hardware, what it supports. Does it has unified memory? Yes. What compute capability it has, what warp size we have, on stream processor, all the information you can read it yourself. So this is where you can compile for this specific hardware. But there is additional the flag. Yeah, that is the one I was saying. If you put -ACC multi-core, you compile a same code which you think you are compiling for GPU, you can compile for the CPU as well. Okay, so it's guaranteed that it will work both ways. Then for the GPU, you just need to add CC80 for Leonardo. I put it specifically, but this can change. Okay, you always have to look at specification of NVIDIA. Before used to be -TA, and now it's deprecated, so you cannot use anymore. If do you know what is pin memory and unified memory? Yes, like if you know CUDA, you know what is pin, pageable, unified memory is. Again, you're not doing anything pinned in sense in your code, but you can ask compiler to take care of this, right? So if you just put pragma ACC kernel, you want memory to be managed, unified memory, you can use just -GPU is equal to manage, and it will allocate, it will use unified memory, similar like what you have in CUDA. Okay, this is, so there's a typo. OpenACC is not OpenACC, is OpenMP, and the flag is very similar. -MP, -MP is equal to GPU, the hardware that you're targeting, all these. One thing that you should always do when you're developing code, adding this one, this flag, -M info is equal to ACC or OpenACC, right? Or MP, or all. All means it will give you all the feedback from the compiler, and it's good to know. It's really good to know, and you will see it will kind of hint you what you need to do next. So this will be your first task. Oh, yeah, this will be your first task. I compile this for multi-core if someone has tried, and if you see, the performance will be almost the same. Okay, they won't be different, but okay, for some reason maybe that thread was free, so it did better job. That was solution. Look, there is nothing crazy, but I can optimize this code, right? Remember, I told you this flag -M info. The reason why I did it, because I want you to, every time you compile, you should read this. Give you one step what you have to do, some sense. Okay, look, the loops unload 8 times, loop not vectorize, copy in. That's what I told before. Pragma ACC gang, so it create team of threads. There's the vector. Look, collapse. I have not put collapse, but compiler did it. So now I can, not knowing what collapse is, I just can copy and paste there, and that's good, right? So if you're using not automatic parallelization, you can use you can use kind of your read the feedback of compiler and try to understand what you can do. Okay, that sort of things. Okay, if you know CUDA, this you can understand what it is, right? Underneath is still accessing the CUDA API. Okay, so there is another thing. I did not put reduction. If you look at the base code, there is a reduction there, right? I didn't ask for it, but somewhere you will see compiler generate reduction as well. Okay, this you have to do it every time you do. Read the compiler. Okay, now I compile the code for write flag, and I can run on a GPU. But look what happened. My kernel and parallel, they both not performing well, right? Something went wrong. So now, as what you like to do, you like to understand what did you do wrong, or is there any other way? I can read my compiler info, which is always handy, because I will go back again to the compiler info and I will show you what it means. But the whole process is profiler driven, right? So that is the loop that you have to remember. You look at your code and you say you profile first time, and you will say this part of the code take this amount of time. Then you know already where you need to expose the parallelism. Then you use OpenMP or OpenACC to parallelize the code, compile it, measure it. You're not happy, go back again. Look, the second step is data movement. You have to express your data, right? Data movement. So if you use that, compile again, measure again. And if you do it many times, you will see, you will find a very well optimized code that you cannot further optimize. Okay. And that would be your, let's say, more performant code. That's what I wanted to say. So you need to, next step is you expose parallelism on the targeted hardware. I'm not calling GPU or CPU, right? You can compile both. But what I want to do is to move the data. But catch, I say CPU and GPU. If you're compiling your code, do you really think to worry about data movement? Yes? No? No, because it's a shared memory, it's just like OpenMP, right? You're not migrating data anywhere, right? It's there. That can communicate by sharing data, by sharing this variable, because they have the same common address space where they can read and write. It's up to you. Make sure that the correctness of the outcome. But we're talking about two different hardware. You're migrating kernel, some task, but also migrating, you need to move the data as well. So there should be other way that I should find out apart from reading the compiler info. So that is where Nsight system, Nsight suite comes. If you just take a picture of this, you will go to the website where you can download Nsight system. There is also Nsight compute. This is the family of NVIDIA profile. Very easy. It's a GUI that you can, you're going to generate a file. You're going to download on your local machine, and then you're going to visualize it. Some of you guys might have experience, so it's very redundant. But if some who doesn't know, it's something that you have to practice all the time. So we are going to look at Nsight system. So that's what you have to type. It's available for Mac, Windows, Linux, everything, right? So all the operating system. It's very lightweight, so you can take advantage. I think there is a Python interface as well. So if you like Python, that's way. This is your moment to sign. Okay. So what I'm going to focus, how do you profile your OpenACC or OpenMP code? Just like this. ANSYS. So first time when you log in on Leonardo cluster, when you ask already the compute node, ask for the compiler, you compile, you have binary ready to run. Okay. Compiler on runtime, compiler already know where the task has to migrate, when the data has to move. Once you have that, you put ANSYS profile -t if you want to trace CUDA, if your application has OMPI, OpenMP, whatever, it will do the job. If you put -start, it will give you the profile session. Also, if you want to know CUDA memory map, this is something that you can read on the documentation. Here it's written. If you don't put minus, you should always put stat true. It will generate kind of summary for you, so you can read it. But we were going to download and visualize. Okay, I'm going to show you some examples. If you don't put minus force override, that means every time you run, it will generate a new file. And that's what I said, it's incremental. You add something, you generate a report. You look at your report, you're not happy, and you understand how long a kernel take when the data was not moved efficiently. You look at profiler, go back, do this. But you came to the point where you say, there is a lot of chunk of file. I don't want to run it all the time. I know exactly what I'm doing. I can do minus force override. It will override whatever is generated. Okay, and you get minus QDRP. This is the extension that NV profile will generate. This is how it looks like. Okay, it will have some of you already have seen this. It has information, thread, core, migration, other information process, thread for both for CPU and GPU. They can look at it. If you use on-site compute, it's different because it's going to just track the GPU event, doesn't care about the CPU. Okay, so this is different matrix, which is also very nice to look at it. When we come back after lunch, I will show you that part when I will show my work. Okay, so then thread states CUDA API, or that means it will give you information about if you're using library, for example, cuDDN, cuBLAS, or if you have a kernel launch, it will give you kernel launch information, how long, what's the percentage the kernel will be executed, or how long it took to move the data, right? That person is also giving. Okay, that's how what you see. You can track multiple GPU, and that's it's given here. Okay, it really helps to work on application. Now I look at again the code. Okay, and now I want to profile my code. Okay, so I see which part of the code taking how long. Okay, and if you there is something called NVTX. Look at NVTX profile, and where you put Pragma ACC loop, you can tag these two. You need some header as well. This will generate for this kernel how long it took. If you don't do, if you look just profiler, you can also see each kernel how long it's taking, and something this similar like what you get here. Okay, why do you care about data transfer? I already gave you hint. The point is that you really working on two different hardware. So you see the GPU internal memory is 900 gigabyte per second. So in this heterogeneous computing, you see the weakest point is, where is the weakest point? Is basically the connection between CPU and GPU. What you get, well, the number is, I wrote because I just copied from some presentation. It was 16 gigabyte per second. Theoretically, you get lower. In some cases, you get 5 gigabyte per second. This is where you transfer the data, right? It has limitation. You cannot, if you try to busy the traffic, for example, like sending data or receiving data, this can be costly. Okay, so make sure when you launch, so the step that you want to follow is like this. You launch a kernel, you move the data when they execute, and they would back. So what you conceptually what you like to do when you launch the kernel, right? You like to move the data the duration of that kernel needs, right? The data should reside as long as that part of the code needs it. Okay. Now, in CUDA, you know, I am more inside, but you see, it's very handy how you can copy in or copy out this directive you can use. But if you don't use anything, and I told you already, if you put flag, you can use CUDA malloc manage. Sorry, not CUDA manage, must manage. So it basically using CUDA malloc manage unified memory. That means although they are physically different, but your compiler is going to see kind of one memory space. That means my data is going to migrate either for CPU or GPU. Okay, so you will see there's a lot of page fault happening there. And if for that means you need to know your code. So if you look at profiler, and you will see where the data is. So if I have a new this, you remember these things that we are computing, right? This stuff. You see, ANU should is right now is residing on the GPU. Use post parallelism. It means that that kernel is going to execute on the accelerator or any hardware. That means you need to copy that data, right? But that means once they are done, you need to copy back. Okay, this is how it's done. You don't want to do every iteration, right? So what you like to do, block those data as long as that loop requires or this kernel requires. Okay, there is a very nice, so that means excessive data movement is dangerous. It can hurt your performance. There is a way to understand. If you put if you set this export ANV ACC is equal to underscore time is equal to 1, you can see other feedback, and you will see something very interesting. If you just zoom it, you will see that 93% time when I just added pragma is spent in data transfer. Okay, that means computation. There are very little time is done for computation, and this is where you want to minimize it. Okay, I told you read the compiler info, and it gives you the hint. You see, it's generating implicit copy in. It's telling you what to copy, then what to copy out. If it's not present, it tells you. Reduction I already told you. But look, there was one kernel launch, but there's another kernel launch, and it says copy in, copy out. Now you already have idea that what all I need after kernel launch is to move the data. I have to manage the data explicitly. This is implicit done by the kernel by the compiler, but now I want to do it. I want to help compiler. I mean, compiler is doing a lot of things. When you are using directive approach, the idea is you should help compiler as much you should. Okay, compiler is always can do magic, but you as a programmer, you need to help compiler to figure out more and more things about your code. So this is what you have seen before. Not going to repeat myself. So how do you manage the data in OpenACC? Just like this. Copy in. Copy means you can allocate memory on the device, copy something host to device, and move data host to device. So that this can do both. But for some reason, for example, embarrassing parallel, if you see C is equal to A plus B, all you need A and B to be copied in. I don't care what happened afterwards, right? I just care about C. So I can use copy in and copy out. What I should copy out? C, because I'm just interested to store the data. So I'm not copying array A, array B. It's useless. Or I can create a buffer on the device, but not copying. So for example, C, I don't need to, I can just create on a GPU, right? I can also use that. There are others present, create device pointer, but this is more advanced. You can look at the specification. Okay. For OpenMP, it's map. So it's a map from host to device. From to one means host, and to means other way around, device to host. Okay. And most of the things are very identical. Now, so that's what I told you here. So here everything looks very simple. All this code will do is just execute things on your GPU. All you need A, B, C, that has to be visible on device, and all you need to do is just add copy in what you're copying, A and B, right? Has been copied, and then you want to copy out only C. After this 2 point, you see, you're out of parallel region, out of data region. That means the information about, so basically A and B will be deallocated, also C will be deallocated from the device. Okay. Okay, so that's what it shows. Okay. Now, sometimes you don't want to copy entire um, uh, iteration space or size of your array. What you want to do, actually split it, and you can do array sharing as well, shipping as well. So you can just put pragma sc dot copy in, you see copy out. I'm just not copying from 0 to n, but I am chunking them. Okay. All right. So that's my code. I launch my kernel, but I'm also copying the data there, right? You see, copy in. I want copy out. Why I want copy out? Because in these two kernel, I need that uh, that uh, data, which would be updated on CPU, but is going to be needing them on device as well. So I can also copy in for this function, for example, C, I need to copy in, and for some reason I'm copying out only in that part A or B. Okay. So one good thing is that you can see that at the same place, I am asking kernel to move the put the kernel on the device, but also move the data at the same time, right? Now that's your task, and actually, if you do that, it would be bad. It will not perform well. So that's the answer. And what I want is to do the last exercise, and then we go break. But when you come back, then we'll see some advanced feature. Can you someone tell me why it would be bad? Again, you need to profile it. So it's good to do this exercise because you see that there is a copy in this one. If I put, I want you to do that. So I give you 10 minutes and try why. So what you want to do, compile this code, add exactly the same way, copy in what you want to copy in, copy out, and profile it with ANSYS profile, and see exactly when the data is moved and how many times it's been used. Okay, so this will give you a hint, and this is how you start to think where to put the data clause so that data can be reside or live on GPU memory as long as the kernel needs it. I don't need to copy every time. That is your answer. If you're not asking ACC to tag, or you're just saying minus MPI and or OpenMP, it will just record the event for the given event, right? So when you say OpenACC, it will record for OpenACC when you loop the pragma. Okay, so make sure that you know this. Okay, so it's something that you will see. You have CPU, and this will be CUDA HW and OpenACC. These are the pragmas that you added. Okay. Okay, so I went through all these things. Okay, so even I added data clause, it didn't go through, right? If anybody did the exercise, you will understand why. Okay, something went wrong. Even I know I am doing, I'm thinking correctly, right? So I launch kernel, I move the data. But now compiler give you the good guess, and this is what you will see. So I just have a screenshot of that. You see memory is 98.9%. So you will see something like a lot of page fault happens. So every iteration, the data is being moved to host and vice versa. Okay. So the kernel takes only 1.1%. what you would like to have to minimize now the memory part. Okay, so that's what I was saying is if you put just this copy in A or copy new like this clause, what you will do is just every iteration it try to data which need to be copied on the device memory, then copy out that on the device. So this is every iteration is happening, and this is not good. Okay, that's what I put it here. So what we want to know is to optimize our data movement. So obvious thing would be to take copy data clause to put really embed a kernel in between, right? So I don't want to launch kernel. What I want to do, I want to copy data first, then launch kernel, right? So that's what you need to optimize. So there is this data construct, which is pragma ACC data. And if you so that's what you did before. That was implicit copy. For each kernel, you're copying for that kernel for this given time, something you're copying, and for something copying out. But after that, you are out of that parallelism. Okay. What you want to do is explicit, where you're moving pragma ACC data copy out. You see, so I'm blocking, I'm transferring my all um, data to the device. Then I have ACC kernel. So I launch two kernel here, and you see when I'm exiting until this point, your data is blocked. So what you get basically two things, right? You get compute reason, that is this kernel ACC. There's a two kernel launch here. It's not necessary. You can fuse them both, and compiler will take care of this. Or and also what you're getting is so I say compute and data bound, right? So you're just blocking that for given this loop, data should be there when the kernel is over. Data either the array that you need to copy on the host, you copy it, otherwise you don't care. Okay, that what means. So here is one time. So what you did, copy data only one time. In this example, for example, you are doing two copy, right? That is expensive. In yours, where you have a lot of iteration, you're doing multiple times. That's what I wanted to find out. Okay, now, yeah, so that is, so you have compute reason and data reason. Okay, this is true for most of the programming standard you want to follow. Okay, this is something that you're bounded in to. Okay, there is another thing called unstructured data. When compiler cannot figure it out, what is the array size is, something can be very complicated. What you can use is called interdata and or exit data. This is basically the same phenomena as you do in CUDA when you are allocating something and deallocating something. Okay, make sure the good thing is that you can put in multiple places. Okay, so you can call them and you can create that buffer for many places. These only four construct work for create. Okay, so you copy in, copy out, and you can create memory on device, but you don't have to copy and you have to delete. Other things will not work, like present or some other things with exit data. Why is it standard? This is what I said. You see here, pragma ACC data create. Okay, then you have pragma ACC data delete. At this point, it's being so you have basically two functions. Here, I'm launching pragma ACC loop, my loop, where it is exposing the parallelism, and then deallocate pointer, whatever you see there. So what's going on in this sub? Look, copy in. I create, I copy, let's say, allocate A on device memory. Then I did B. I delete A and B because I don't need them, so I free the memory of on the device, and I copy out only C. Okay, that's what is compiler is doing. All right. So difference between structured and unstructured data. Unstructured data can have multiple starting points, as I showed you one of the example. Can have multiple branch, and you can exit in a multiple delocation as well. You can do that. With here, you cannot. It must be in a single function. Okay. So if you're calling multiple function in structured data, you are not allowed to. If this is just standard of OpenACC. So if you are using structured data and or if you're doing copy in, as I said, compiler will kind of ignore it. So make sure that you use other clauses as well. So this is the exercise that I wanted you to do, basically looking at how structured data and unstructured data would be. And I think you should try to do at home, maybe if you want. What I want to show is that if you optimize, you see kernel first time when you put data reason, and now you see your data optimization. It's really fast, right? And again, that's there's a typo here. Now you see things are reversed because now memory is only 5.6%, and most of the time has been spent in kernel, right? This is just a typo. But you understand, this is what sort of things every time you have to do. You have to see how long kernel being launched, is many times page will happen. That means there's a lot of data transfer happen. I'll make sure that they minimize data movement, and that is the let's say main part. Then there is the data synchronization, something called Pragma ACC update host. That means for compiler, it understand that scope for the device is out, so this need to update on the host or device, vice versa. Okay, so it's one is the device perspective, where this is the data needs to be updated on the host. For example, host A, that has to in the perspective of device. For device is other way around. Okay. Yeah, so you see, you can do the transfer between data host to device, just like this. All right. If you do that, you can implement with the same solution, just declaring, creating a buffer for on the device. Okay. And you can update value of A right here, Pragma update that is on the device. And you see at the bottom where you have Pragma ACC update host, where the value of A is being updated. Okay. And you see they more or less perform the same, but it does better job. Okay, so now this was the first part. I want to go to the second one, where I want to show also some of my work. What I showed you two things. First, what I talked about, launching kernel, optimizing data, but I have not talked about how you can optimize loop. And you have to remember when I say grid, block, and the core, right? I'm coming back there. So CUDA, in three slides, I will explain you what CUDA is. Not really, but more or less what it does. So when I say kernel, the function that you launch on device is called kernel. Okay. So when you launch kernel function, that will be run by lot of threads. Like each thread will work on different data element, right? It's SIMD, simple single instruction multiple thread. What CUDA will do? It will launch a block of threads, but in order to let's say have more parallelism, it try to group in warp. Okay, remember zero is a group of 32 threads. I told you in the beginning. This is what you do. This is on NVIDIA GPU. AMD GPU is different. and each there's a limitation on each thread of blocks is 1024 thread you can have. In order to map correctly, you need to compute this, and CUDA is just one line this, and then you manage your memory. You need to create, you need to know what is the index of each thread is, which blocks they belong to, and what is the dimension of block. Okay, this is in one line what CUDA means, and that's the execution model is. You see, there is a qualifier, global, global. Why I'm showing you? Because you will see the next slide, the translation between OpenACC and OpenMP is very simple. You don't have to do all these manual changes. Underscore underscore global, this is qualifier, is basically a directive to tell compiler to generate machine code which for the accelerator. Okay. Then here I'm just using CUDA malloc manage. There's some pointer, some size. I'm just making sure that when page fault happen for CPU, that data should be available. At the same time, if the function is running on the GPU, the data needs some function can be available. So I'm managing this data, not copying manually, let's say. But then this is very important because I'm launching kernel that have been add vector info, but then I'm dividing in number of blocks, number of threads. Okay, and that matches to the hardware. So you want to utilize how the parallelization level of parallelization that CUDA offer. Okay, this is something that if you know CUDA, you should know this. How do you do an OpenACC? That is our attention. So yeah, so that is more or less what you saw in equation in C, but that's what you have. You launch a kernel, you have a thread. Thread is grouped to the warp. You don't launch one warp, but you launch multiple warp, that is block. Okay. In OpenACC, yeah. So that is GPU thread hierarchy that I said it before. You have GPU, which is consists of thousands of this grid. You have multiple processors. Block can have maximum 1024 threads. Why? Because the hardware can support and optimize its parallelization better. Warp can have only 32 threads on NVIDIA GPU. AMD would be different. And this is the translation between OpenACC and CUDA. That's why I had to go there. So gang is your block, worker is your warp, vector is your thread. Okay. It just map correctly what hardware support. Okay, so this is good because to know that if you are AMD GPU, it's called work group, wavefront, and thread, but it's exactly the same thing. But in reality, what you're doing, you're launching this number of threads. Okay, doesn't matter which hardware you are, which platform you are. So how do you understand? It's illustration done by OpenACC community, and it's like this. So if you have to paint your house, and you have this brush, right? You can do it, but if you have to do this entire building by yourself, it's not, let's say, it's not feasible, right? You could do it, but in a year or 2 years, something like this. So what you like to have more people because you want to do things fast. Even you are alone and you put your brush bigger, it still will take more time. What you want to have more number of people that can group together and work on different part of your building. Okay. So you organize worker as a gang. So one gang works on this side, this side. Gang is just group of this human that they're working on, and they work all independently. Okay, that's the one thing. So that's illustration. So you see you have worker, vector, and there is three. You have basically three worker. Again, you have to remember block. I had forgot. block, warp, and thread. Okay, that is the where vector um, gang and vector and these things come from. Okay, so but the one thing is that you have to do like this, the parallelization. So what you want is to put gang, if this is 3 nested loop, you want to put pragma ACC loop gang first, then worker, then vector. Okay, that is and this is done like this because you have seen vector is basically the lowest level of parallelization you can have. When compiler will launch, it can, if you're not defining how many number of gangs that you want, it will create one or multiple gangs. Okay. So vector is the lowest level of parallelization. Every gang at least can have one vector, but you can also specify, and there is a cost of that. Normally, what you want, you let compiler to decide. You don't do that, right? Unless you exactly know what you're doing. How? So first, how you control them? You did in CUDA, where you said, I want to launch this number of blocks and this number of threads. You did it, right? You computed correctly. At least a block can have at least one thread if remaining work or data requires to be done by some thread, right? So one block can have at least one thread. So that's why you did the roundup in CUDA. Here you can control with number of gangs by like number of gangs, number of worker, defining number of length. So it's an illustration. So look at this. Launch a gang has only one worker. What you have is basically what compiler will do. It will launch 4 worker and 4 gangs, and it will vectorize with 8 length. Okay. Now what happens? So it will go on and it will do computation, but I can have still for this I can still generate 4 gang, but now what I'm doing is actually instead of having 8, I'm asking 4 vectors, so I'm splitting it 2, right? So I can do this as well. But what happens if you have loop which is the inner loop is just go from 0 to 4, but I ask more vector? What happens is that you're wasting resources, right? So worker will vectorize that part, but you see only 4 let's say 00 to 003 will be utilized, but the rest of them will be unutilized, and this will be could hurt the performance. So unless you don't know, if you don't know what you're doing, just let compiler to do the job. Otherwise, if you exactly understand when how many vector length you want, you can add it there. Okay. Okay. So for example, this is another one. You can have 2 worker, and I can have vector length 4, and then this is does this job. That is where the idea comes from tiling. I can have a 2D matrix and I can tile it, and it's something that I've been talked yesterday as well, and also today. So OpenACC support tiles as well. You can define the number of tiles in each direction that you want. There is another thing is collapse. The title is wrong. Collapse. You heard it what collapse is, right? So in OpenMP, collapse is like when you have a 2 or 3 loop. What you want to do, what compiler does is basically fuse these 2 loop in one, and it chunk it. There is another catch. In OpenACC, if you are collapsing things, so let's say for I is equal to 0 to something, and you're doing some computation, and then for j is equal to something. If you try to put collapse, compiler will ignore it because there is some edit. So what I meant to say, OpenACC is a tightly nested loop. It means I and j, it should be, there is no other things should be given, no other instruction should be given. Okay, that's another thing that you should know when you are using OpenACC. Okay, reduction. So in your code, you saw max 2 colon error. That is reduction. That reduction is just either you want to add some one scalar value or array, something that you can do. In CUDA, you have to follow some algorithm or something else, but in OpenACC, just adding reduction, just like OpenMP, will do the job. Okay, so that's a lot of things that you can do. Independent clause. So what happened? I told you that you are in the hand of compiler, right? He's it is the one, she's the one, or he's the one who's driving the car. So what happened is that you think that the loop should be parallelized, but it can completely ignore. It is not easy for like this, not easy to understand for compiler whether it should be or able to or not. But you as a compiler, you a programmer, you understood that no, this loop can be parallelizable. What you do, you put independent clause. That means now you give instruction to compiler that you should the loop is safe to parallelize, and you should do that. Auto clause is the same, it's just reverse. Okay, it's just opposite of independent. There's also sequence clause, which tells compiler to loop run sequentially because on parallel hardware, because for some reason it's not efficient. We'll just do the sequencer just like this. If you have this this inner loop, I want that the last loop should just do sequential. It shouldn't be optimized. It shouldn't be parallelized. So it's like this loop. Actually, there's something mistake there, but the example says like, so what happened is that you have cache friendly ij and you're moving k, right? You don't need to parallelize the inner loop. You just put acc loop sequencer. Then there's a private. You heard it before. You are in shared memory for some reason. Well, you are using shared memory, and you can make sure that if the variable need to be private, you put private clause or first private or last private. Well, most of the time you use first private. It works. But you see what your program requires, then just set it up. All the exercise you'll do it at home. Just I optimize loop. Yeah, sorry, this is the correct one. So I told you that I'm changing the number of worker, and I try to change how they evolve, and you can see for worker 4 is the highest things I got. So far was good when you understand how many ways I can optimize our code: data movement, loop parallelization, understanding that whether I should use independent or not, or sequential, I need to use it, etc., etc. So this is all the detail, and everything is done on single GPU. Now, how do you use multiple GPU? And I think we will finish early. Okay, multiple GPU. There's a two-way. So it's not that you have only one single node with single GPU. Like Leonardo has this complicated connection. So one node can have 4, depending on the which SPC system you are using. You can have this connection which every node is connected to. So how do you launch? How can you use multiple GPU using OpenACC? There's a two strategy you can follow using MPI, and I'm going to illustrate one of the project that I did. Why I want to put that? Because what I told you was sufficient to put the code, right? Most of the code, you know what MPI is, how MPIs work. Now you understand how you can code the code. And then you can do multiple threading programming model. means that using OpenMP, creating a lot of threads, each thread can do migrate to GPU, do some specific tasks. So you can assign this thread. So you have to worry about thread affinity for each thread. The GPU should be attached to that threads. So what I'm going to talk about is ACCM, which is it's a code which is a space plasma physics code, and it was done. This project was in collaboration with E4, Elisabetta Boiler, Maria Elena Innocenti, professor from Ruhr University, and we have also professor who just died. I mean, it's the first time I'm going to give a talk without him. So Giovanni Lapenta, and then we have NVIDIA guys. Especially, I would like to thank Filippo. I think we learn a lot, and actually, this project actually wouldn't be possible without his help. So big thank to him. So ACCM is written in C, C++, and all he had is parallelization with MPI. It scales fairly well, and you don't need to know so much things about this code. It's just you need to know that he has a moment gathering, particle mover, field solver. These three modules we have. All three modules could go on GPU. For time being, we just have moment gathering and particle mover on the GPU. So I said, profile your code. That's the first step you do as a junior programmer or developer, right? Look, you tag or you do some kind of benchmark. You run with 4 MPI task or 35 MPI task. You see, one thing is the green part, which is moment gathering, is the one module takes 80%. And this is true, although you reduce the time, but it's exactly the same percent as the first one. So the simulation was done 128 cells, 6,400 particle per cell. This much iteration was Marconi Cento, our previous cluster, right? So all I did first, we take the particle module without knowing anything what we should do. We look at the loop, which we know that there's a lot of computations. Just add pragma ACC parallel loop first time, right? Then I profile it. This is why I told you, you have to follow this. And if you take NVIDIA Bootcamp, you have to go through this pain. There is no way out, okay? So download the profiler first and then produce this. Now, there you go, here. I look my profiler and I say, oh, there's a lot of page fault happened. So you could say, I expose my parallelism, now I want to add data clause. And I said GPU computing is hard, because if your code is written in such way, so one of the problem of the code was the CPU code was not well optimized. So we had to optimize it. It was a very complicated data structure. We have to unroll some loops. We have to simplify things. We try to add data clause. Guess what? Result code compile, it crashed on runtime. We didn't know why. We understood that C++, you're using some complicated template, and for some reason, for compiler, it was not easy to understand what to do, right? It generates some binary, but it doesn't matter. It didn't work. What is the way out? This is bit advanced, because I just talked about OpenACC. I didn't talk about the relation between CUDA and OpenACC. Okay, neither MPI, but just highlighting things. We use CUDA mean prefetch async destination to device G. When you put the 0 on the device, we move the data using CUDA API, and it works. Okay, so knowing things, how to solve the problem without changing much, but still we are using to expose parallelism. I'm still using OpenACC. Okay, this is so OpenACC was good enough, but we didn't get so much significant improvement. But we take the module which is Moment gathering, which is an additional thing. Again, there is atomic operation is happening here. It worked pretty fine. We add some pragmas there. Then what we did, we add CUDA memfetch. We are managing memory with CUDA API. Okay. Now, apart from ANSYS, I told you about N-side compute. At some point, ANSYS is good, but you want to know a little bit more about GPU event, because N-side is actually you are still tracking CPU, GPU, and all things. You want to understand what exactly happening to GPU, right? So one thing you know that application can be memory bound or compute bound. Most of the scientific computer code, even you see OpenFOAM, is highly memory bound. Axim is highly memory bound. OpenGadget is highly memory bound, because this is how algorithm is. If you look at OpenGadget, where is follow the tree model, which just look at which is my my neighbor. So it's searching only the memory access. So you spend a lot of time, and you're bounded by this moment gathering. But what is interesting is N-side compute give you one thing. It tells you how the arithmetic intensity clock per byte as a function of performance clock per second. This is what theoretical curve is. This much what your hardware you can reach, and that should be your goal. You are using OpenACC, you might never get it, but can you be as close as possible? That is the challenge. We were here. Now we move that side. What is the difference? The first time we did, we had a long stall scoreboard. That means there are more things were loaded in the memory, GPU memory. That was absolutely not efficient. Somehow we needed to manage our memory as well, and we wanted to have more computation. By looking at this, and if you use learn on NVIDIA documentation, it's quite descriptive. It tells you which part of the code you need to optimize. Actually, you can just click it and it put you there. So it gives you a lot of hints. That's why development profiler is, or profiling your code, it's integral part. You cannot go away from that. Now, what we got? We just put two models there. Look, we got 12% of speed up. Even we did the benchmark for CPU version code and actually improved because we understood what the problem was. Now, this is the same graph that you have seen before. 4 GPU, 4 MPI task. Look, I got 5x speed up. I'll show you something that we did with this existing implementation. That is that we run our code on different newer GPU. Good news is without any problem. And we see newer GPU actually give us a better performance. So just so B100 Cascade, when A100 and Grasshopper. Even Grasshopper, the newest GPU, we didn't change a single line. And that's where we were very happy. And our next goal is to try GH200, what happened. That is on multiple nodes. So here, Grasshopper, we just use one GPU per one MPI task. That was very simplified, but I'm sure what we are confident, the next thing we're going to do is to understand what happened when you try with multiple nodes. And I think it's going to be better. I mean, now Grasshopper for one-to-one comparison, we have already 12x speed up. So what you learn, this is what we did, full application. You didn't need to know more than that. You want to learn CUDA? You want to know anything else? Or this is done all 6 months. One hackathon of Chineka, done. Okay? That's my strong scaling and weak scaling. Strong scaling, 72% efficiency up to 32 GPU, 80% on 1024 GPUs. So far good. Leonardo, not sure is good. I still have to try, and you know already, I'm this system is not that easy as we think, as Marconi Cento. I always find I'm always so satisfied by my own result, so I can't tell others what if it's good or bad. But anyway, on 1000 GPU, you still have 85% of, and this is the best case that we got. And many trials, many tuning. Strong scaling is still struggling. Weak scaling is it's okay, but I want to repeat it again to make sure that we have more or less what Marconi, at least better than this is what we expect. Okay, multi-threading. It's complicated. Why? You have directive. You are telling compiler, uh, go create a multiple thread. So what you want to do is query the number of available thread. Set the you see there is a lot of manual operation that you are doing. Will acquire the number of device, compute on GPU. Then you are finally assigning GPU for you are setting up device for each device. So basically, one thread can attach to other GPU. One thread can do other GPU and do something other task, right? So that's the way you can use multiple GPU. The final thing is if you look at the same code that you have, where you have two loops, I and j, you have to just manually make sure that your start and end is chunked correctly and assigned correctly. You're no overbound on the iteration space. Okay, so those things that you have to manually take care of. Other things you learn, update and self. I need to put some kind of barrier because this is asynchronously updating, so it can go. You see, there is many places can go wrong. So that's why these very little things with multi-thread and if you can do. I mean, not people can do. You can do a lot of things, but if it's easy to do, that's fine. OpenMP critical, that's another barrier. Another barrier. When you put all this, it may not be that your application is efficient. MPI is good enough. MPI GPU is the way to go. Where you can learn more about OpenACC. Scan this too. Go to openacc.org. They have bootcamp almost every 6 months. It's a bit advanced, so you need to know this class might be useful. NVIDIA training, that's another good source material. I learned a lot from them. Where we are going towards, now we understand GPU. Is it good enough? Is OpenACC, we are happy for future? No. You already talked about quantum computing. I know nothing about quantum computing. So, but in future, something can come up and you need to, when you change the hardware, you need to adopt a new standard. You have to prepare for this. You have to update your knowledge. There's no way to go. Okay. In future, you might have cluster which complicated hardwares as well, GPU, quantum, QPU, TPU. Depending on your need, you can just feed them, right? How you use them, what is the best way to, and it could be that you are going to use, or there can be HPC scenario where you say, I have this problem, I need this partition, which use just this GPU, or I need TensorFlow, so it's just CPU. For machine learning, I don't need to use this, I need to use that. Or some hybrid quantum computing, I need that. So you would just be surprised what is coming next following years, okay? And apart from thanking universe, I think I thank all these people because I learned a lot from them. And apart from this, This is where I am done. And if you have any question, I'm here. Question? Yeah.
Actually, just a quick question
Yes.
about the moment where CUDA mem prefetch async where it was used. It was necessary, or there was a workaround with the practice?
It was workaround because so the compiler that we're using, so there was two things, and we didn't dig out also. So let's say we did workaround. We know what's it was complicated to change in the code there, so we have to rewrite some part. We were lazy. Second part is that maybe that no, that was a workaround.
Okay. So it is possible to do that just with the OpenACC or no?
You can have so you can use CUDA API, okay, plus OpenMP plus OpenACC, okay. This is just to showcase that you're not just you are allowed to use OpenMP pragmas or OpenACC pragmas with CUDA, also HIP, okay. Also Vijay was telling me that you can also probably you can use SQL plus OpenMP as well. So there is the point is like, what is the effort required to offload my code as easy and less time possible? As the scientist, what you want to solve a problem, not spending time, right? That is the effort.
Thank you.
Any other question?
Yes, please.
Maybe I didn't get the way you improve data locality in
Yeah.
your application,
Mm.
since usually you have to redesign the algorithm in
Yes.
some way.
Yeah. So data locality is something that, so for example, you change the loop order. So instead of going ij, we just change the loop order of ij. This way we can index data locality, but that can improve many ways, right? So if you are calling some global variable, can you move? Is it possible to have in the function can temporary function can be the local to the, in our case, we change the loop order and we unroll the loop. That is the main two advantage. Exactly. That's true. That's true.
So if there are no other questions, let's thank again our speaker, Nathan Shukla, for a very interesting talk.